Did you know that if you consume more chocolate, you're more likely to win a Nobel Prize? How about the fact that people with later bedtimes have shorter life expectancies? And people with larger shoe sizes have an increase in reading ability. These are fascinating relationships, but can you say that we should all eat more chocolate, go to bed earlier, and wear bigger shoes? Not necessarily. All of this data comes from correlations, another type of research in psychology, but one that does not necessarily indicate a cause and effect relationship. For our last section on research practices in psychology and data interpretation, we're going to go ahead and take a look at correlations, ethics in experimentation, and statistics, the last piece of data interpretation that we need for psychology. But let's go ahead and start with correlations. As I mentioned earlier, there are some things in psychology you can't necessarily do experiments on, probably because they're unethical, like taking a look at parenting styles and self-esteem. We would never intentionally have parents change their parenting styles to see if it has a positive or negative effect on a child's development. That would be highly unethical, especially if we think a specific parenting style would have a negative effect on self-esteem. But we can, however, see if there is a relationship there by taking a look at parenting styles that already exist and seeing if there is any relationship that exists with a child's self-report on self-esteem, for example. These are what are called variables of interest. They are specific things that researchers want to look at to see if they can examine it in a study. Having someone answer a survey where they're answering questions about self-esteem, for example, would be known as a self-report. Now, when people do self-reports, as we mentioned before, there are things like social desirability bias. There's also self-report bias, and that's the tendency for people to present themselves in a favorable way about their behavior or their attitudes. So we need to keep that in mind when we're examining those variables of interest. As we dive into what correlations are, we also have to deal with the directionality problem in correlations, that we don't necessarily know which is the cause and which is the effect, and how these two variables are related, or the third variable problem, where there's something else entirely that's influencing these two other variables. Like, for example, if we go back to the later sleep schedule and life expectancy, it could be that there are other health factors that are considered third variables in this study that are both going to impact a person's quality of sleep and their quality of life that could impact their life expectancy. So what are correlations and when would we actually use them? Correlations are basically a statistical measure, and they indicate the degree to which two variables are related. Now again, correlations do not imply causation. Only experiments can imply cause and effect because we're manipulating variables. But we can see predictive value in correlations to see if one can accurately predict another variable. Now, we will not have to calculate correlation coefficients in AP Psychology, but it is helpful to be able to see correlation graphs or see a correlation coefficient and be able to say what it means. Correlations are measured with the letter R because that indicates relationships. And the number is going to be anywhere between -1 and +1. The closer it is to a whole number, meaning the closer it is to -1 or +1, the stronger the relationship is, meaning as one factor increases, the other's increasing at about the same rate. Or if one is increasing, the other is decreasing at about the same rate. That would be a negative correlation. The closer a correlation gets to 0, the weaker the correlation is, meaning we can't accurately predict where a variable will lie if we have information about the other variable. There are a variety of examples that we can use that will demonstrate that, but think of cars, for example. If we look at the miles on a car and see that they increase over time, we might also see that the value of that car decreases over time. So as one increases, can we accurately predict the other variable and the rate at which it's decreasing? That would be a negative correlation. If we look at the number of accidents a car has and the car insurance rates, those might be a positive correlation. The more car accidents you have, the higher your car insurance is going to go. We can accurately predict that. But if we look at something like the value of a car and the color of the car, that might not have any correlation whatsoever. There are a wide variety of cars out on the road in different colors and of different quality. And so by knowing one, we probably cannot accurately predict the other. So if you were to see either a correlation coefficient or a correlation graph, you could read that data and be able to explain what it means. If the correlation coefficient says something like R equals 0.89, we know that's a strong positive correlation. As one is increasing, so is the other factor. Or if it's negative 0.92, we know that as one is increasing, the other is decreasing. And those are pretty strong relationships. If it's negative 0.05, we know it's a very weak correlation. We know that there's not a lot of predictive value of whatever those two factors are that we are looking at. As we mentioned before, it's important to keep in mind that there are other things that can impact the relationship that we see between two variables. It might look like there is a relationship between those two factors, but something else altogether may be causing that outcome. And that is what's referred to as a third variable in correlations. Sometimes we also see correlations that look like correlations, but aren't actually a relationship between those two variables whatsoever. And those are called illusory correlations. They're like illusions. They don't actually exist. So correlations are just another way that we can collect data in psychology in order to see if a relationship exists between two factors. And these are especially useful if we're trying to look at two factors that we cannot ethically manipulate. Speaking of ethics, let's go ahead and take a look at what you can and cannot do when it comes to an experiment in psychology in order to follow ethical guidelines. If you want to conduct an experiment in psychology, you'll have to submit your experiment request to an institutional review board, or an IRB. Institutional review is the process of evaluating an experiment for the ethical implications to make sure the participants in the study are protected. And there are a couple of different ethical guidelines psychologists must follow. The first one is what's known as informed consent. In informed consent, a participant should be told what is expected of them in a study, what is going to take place, what they'll be asked to do, and you will get their voluntary agreement to participate. This also includes the right to withdraw from an experiment at any time if the subject chooses to do so. There's also something called informed assent, which is similar to informed consent, but this applies to when someone can't legally consent to participating. So like in the case of minors, if we wanted to do an adolescent sleep study, we might need to get permission from the parent or guardian in order to conduct that study. The next ethical guideline is protection from harm, and that is simply ensuring the participants are not exposed to unnecessary risk or discomfort. We know that sometimes there's going to be some discomfort in an experiment, or perhaps there might be some deception involved when it's necessary for the experiment, but making sure that there is not undue risk in an experiment is something that the IRB will take a look at and determine if it falls within those ethical guidelines. Third is confidentiality, making sure to protect the anonymity of the participants and that information obtained from the experiment is not disclosed without their permission. As mentioned before, there is also the question of deception. Sometimes deception is necessary. When you are giving some people an independent variable and others a placebo, the placebo could be a form of deception. But they should know that there's a chance that they could receive a placebo in the study. Anytime you use deception in an experiment, it should be justified by the study's value. If you cannot justify it, you should not be using deception in an experiment. And once the experiment is done, it is important to debrief, meaning once the study is completed, informing the participants of the purpose of the study, if there was deception, what that deception was, and ensuring the well-being of all the participants at the conclusion of the study. So those are the ethical guidelines that we have to follow, and if we cannot successfully do so, we might not be allowed to do an experiment. Last but not least, we're going to take a look at data interpretation. Because once all is said and done, in order to make sure our experiments are valid, or if we are looking at the results of any kind of study, what that information tells us, of course, needs to be meaningful. There's a lot of different ways we can present data in psychology. We might take a look at it in the form of a table, where we are inputting data points, a graph, a chart, or a figure in the case of some kind of diagram. We see these a lot in the publishing of research studies, depending on the subject and what is being researched. A common way to analyze data in psychology are through the measures of central tendency, simply the mean, median, and mode. When reporting out on what we have found in different types of research, we might want to see what the average score was, what the median or middle scores were, or where the most occurring or mode responses were. This helps us to generalize on those trends that we see when we are collecting data. We also can see the differences amongst the data, and that is what's known as variation. When we want to see the difference between the highest and the lowest score, for example, that's known as the range. Or if we want to see where one person falls compared to everybody else being studied, we might want to find the percentile rank, and that is done through the normal distribution curve. In a study where the mean, median, and mode are all the same, we will find what's known as a normal distribution curve. This is a great way to be able to take a look at data to see where one person falls compared to the rest of the population. There are percentile rankings that go across a normal distribution curve that you'd like to be familiar with. Going from left to right, it starts with 0.1, then 2, 16, in the middle is 50, then 84, 98, and 99.9. This is what's known as the standard deviation in a normal distribution curve. So again, we can say where one person falls. So we know that if someone is in the 99th percentile on a test or some other type of score, for example, we are able to say where they are compared to the rest of the population. When someone's in the 50th percentile, we know that they are right where the average score is, because that is where the mean, median, and mode scores are as well. It's where most people fall. Normal distribution curves can be measured in a couple of ways. One is known as the z-score. Again, if the average score falls in the middle, that z-score is going to be 0. It's kind of like our starting point of the average score on some type of measure. And every time someone goes up or down one standard deviation, we can report that by saying what z-score or what percentile they fall into. So someone who is one standard deviation above the mean is going to be at positive 1 of a z-score, and that they're going to be in the 84th percentile rank. If they are 2 standard deviations below the average, they are at a z-score of -2, and they are in the 2nd percentile. It's just another way of reporting where one person is when we are comparing them to the rest of the population. That way, when we know what the average score is, let's say for an IQ test being 100, and we know that the standard deviation is 15, every time the score increases by 15 points, someone moves up 1 standard deviation or 1 z-score on the normal distribution curve. That helps us to be able to say that if someone has an IQ of, let's say, 145, we know that they are 3 standard deviations above the average. They are in the 99.9th percentile of IQ, that their IQ is higher than 99.9% of the population. Whereas someone who has a z-score of -1, we know that their IQ is going to be 85, and we know that they are in the 16th percentile. We will see this in different units throughout the year as we take a look at data. Again, IQ is just a very easy example to see when we are comparing one person to the rest of the population where their scores fall. Now, all bell curves are not going to be normal distribution curves. Sometimes we experience what are known as asymmetrical bell curves, or skewed bell curves. Those can take place typically when an outlier is changing the average data. A positive skew, for example, is where there is one really high outlying score that's going to increase the mean above the median and the mode, and so there'll be this really long tail pulling this data towards the right. Think about if there was a single house built in your town that was worth millions of dollars more than the average home in that area. The average home price would increase, but most of the homes would stay around that same area. So we would see most of the data still to the left, and that multi-million-dollar home, being that far outlier, is going to pull that data to the right. On the other side, we have a negative skew, where there's one very low score pulling the average down, and it's going to pull that data to the left. In a negative skew, we might see that in something like golf scores. Let's say there was a high school or an amateur golf tournament, and all of a sudden, one of the best golfers in the world shows up to participate. In golf, the lowest score wins. And so that professional golfer might shoot something like 20 below par when the average score was 3 below. That one really low score is going to lower the average scores for all of those golfers, even though most of them, the median and the mode scores, are going to be much higher than that one professional player. So we see this long tail pulling it to the left and lowering the average for those scores overall. And sometimes we'll even see what's known as a bimodal distribution, where we actually see two modes. So there are two distinct peaks where most of the information falls, as opposed to a single mode where a normal distribution would take place. And last but not least, we have what's known as regression towards the mean. And that is this statistical phenomenon where when we do see those extreme scores, they tend to be closer to the mean the second time around. This could be in the case of a test where the second time you take it, you know what to expect. The first time might have been more difficult, and the second time may be a better reflection of what you actually know. That reflection is referred to as regression towards the mean. And again, there's different types of data and different ways that we can interpret it in psychology. In looking at correlations, we can look at scatter plots or correlation coefficients, and we can describe the strength of those two variables and the strength of that relationship. We also have in experiments, though, things like effect size and statistical significance. Effect size is essentially saying the impact of the experiment's effect, meaning, does it actually make a significant difference? And this also applies to correlations as well. For example, there is a strong correlation between birth order and IQ, and that firstborn children tend to have slightly higher IQs than the rest of their siblings. However, the effect size is very, very small. We are talking about 1 to 2 IQ points, which is not a very big difference as a whole. And so while we might see that there is a correlation there, the effect size is saying it doesn't really make that big of a difference. The larger the effect size, the more we know that it's making a difference. So if there's a large effect size in an experiment, say between caffeine and memory, we know that caffeine has a significant impact on memory, and that memory increase is going to be quite large. There's also what's known as statistical significance, and that is a statement of how likely it is that we got those results due to chance or due to what we did with the independent variable in the experiment. Meaning, if an experiment is statistically significant, it is because of what we did in the experiment that we got those results, not due to a confounding variable or something else that could have influenced the outcome. We know that that means our experiment is a valid experiment and a good experiment if the experiment is statistically significant. We can create claims, policies, or norms to improve outcomes for individuals moving forward. So by creating a claim, we can create a statement that then provides evidence to say, this is why we should see this change, and those can help us to create new policies or new norms in our societies that will make things better for all individuals. And really, that is why research in psychology is so important, Because if we can prove what we think we know about the way people think and act, and actually use evidence to support that, we can find ways to affect change in our society that will improve people's well-being moving forward, whether it's their mental health, or their memory, their perception of their self, or their well-being. And it also just helps us to understand ourselves and others so much better. So let's start diving into some different areas in psychology and see how we can use this information moving forward to affect some positive change in our lives. Thank you so much for watching, and as always, remember, be kind to your mind.